All right, so unfortunately, we did lose the first video, so we're just going to do the second part. There's other people watching this on YouTube, because I know there's some people outside my classes that watch this that need the first part. Just leave a comment. So as always, guys, just watch. Oh, it's a 4-second video. This is probably just the logo. Yep, periodicity. So periodicity is this idea of them repeating. So I think I mentioned this before, was this idea that the unit circle is always repeating. So if we go 360 degrees, it's going to repeat again after that. If we were to graph a unit circle, so let's say we were graphing cosine. Cosine starts off at 1. Then it becomes 0 at pi over 2. So at 90 degrees, because remember, 80 degrees is pi. So if we were to graph this in terms of pi, what happens is right at 0, cosine already starts at 1. The x value is already 1. By the time we get to pi over 2, it goes down to 0. When we get to pi, it's at -1. When we get to 3 pi over 2, it's at 0 again. The x value is 0. And eventually, when we get to 2 pi, it goes back up to 1 again. That's usually how I graph these, is based off of the halves and the wholes. And then after that, we would notice that we go around again. So this circle keeps repeating. So that's what a period is. It's this repetition that keeps going on over and over and over again. So we're going to talk about how this period can become a lot smaller, or how it can become elongated. And it's kind of the opposite of what you would think. So if we, for example, if we had 2 theta for cosine, you would think that this means that our period becomes longer and stretched out. But what actually happens is, because it starts acting a lot faster, it actually gets half as skinny. It goes faster. If it was 1/2 theta of cosine, what would happen is this graph becomes a lot longer. It starts acting half as fast. So this is what we're talking about with trigonometric functions. We can actually use trig to just show that it keeps repeating. They're called I don't even know how to spell it. Sinusoidal functions. I think that's how you spell it. I have no idea. But it's this idea of an oscillating function, something that keeps going over and over. Usually we talk about sine because it starts at a base of 0 and it comes up and back down. All right. And all right. So that's this idea here. Now, the only difference is, we'll notice that it doesn't go to the negative. So that can be done as well. For example, we can just move a period up so it never becomes, or sorry, we can move a trig function up so it can never become negative. But having it with these perfect straight lines, I think is just different. All right. So let's see what we're doing. So again, here's our sine function. It starts at 0. So sine, if we look at a unit circle, at 0 degrees, our sine value is 0, and then it goes up and down and up. Cosine starts at 1, like I showed before. And then let's get to work on this unit activity. So this one, first form an idea of what a trig function looks like. All right, so if we look at this, are we literally just doing periods? We're going to use this graphing tool. And we want to graph functions. So if you're lazy like I am, copy it and paste it and graph new equation. So we can see that, and we see it keeps repeating over and over and over again. So let's change the scale. Let's start our x-axis at 0. We're going to go to 10. And we want to show this. So like I mentioned before, our, oops, nope, that's not what I wanted to do. I'm going to remove one of them. And I'm going to keep closing this in. So we know it goes by pi, so I'm going to see if this works. Oh, it looks like it does work. Oh, but it's only considering it 2, not 2 pi. All right, so I don't know how this is going to help us. If you guys ever have to graph, I already see the flaws in this. This is really bad. Use Desmos. Desmos is just way better at graphing. And I'll show you how to use the tools too. So let's say I'm doing sine of x. This is going to keep repeating. The way you would change this is you would go to this little wrench. And if you want to change your x-axis, you're going to go here to x-axis. Boom. And if I want to do this, I believe this should work. If I type in pi, it actually changes it to 2 pi. And we can see that's perfectly there. It perfectly starts right at that 0. If you want to be a little more specific, what you can do is give it like one more room on both sides. So because I gave it one extra room, we can totally see that it fits. So this one, pretty simple. We're just going to say 2 pi. It keeps repeating every 2 pi. I believe that's how Admentum wants us to answer it. Oh, it's telling us to look at it. So, all right. So there's that. This one we know is 2 pi as well because they just showed us this. So I don't know why they're asking us. What is this? We already gave you the answer, by the way. Let's look at tangent, though. I haven't really gone over tangent, so let's see how tangent looks like. Tangent, it's something different happening here at tangent. Let's see if we can figure out what that asymptote is. So I'm going to say the asymptote is at 2. So I'm going to make this line x equals 2. And it looks like that's not enough. All right, so that's kind of weird. So what if I say the asymptote is pi? That's even worse because pi is 3 points out. So what if it's pi divided by 2? That looks more spot on. We can see that it's getting really close to there. So it's pi over 2. Let's look at this, our left bound one. So what I'm doing here is I'm just making a vertical line by saying x equals something. So let's try x equals -1. Oh, that's cutting it. Hey, it's Nick. Yeah, I don't like how people keep asking me about my pop figures. Oh, great. Now it's on YouTube. Thanks, Nick. Thanks. So I'm going to try -pi over 2. So if I see here, I'm like, oh, cool. It goes from pi over 2 to negative pi, or I should say, it goes from -pi over 2 over to pi over 2. Again, we can see that it never touches this pi over 2. In theory, it would at infinity, but infinity is a theoretical number. So that means that this period is pi. Am I going to have to tell your mom to like spray you with a water bottle like every Monday and Wednesday, Nick? I, oh. So here's another one, guys. So if we look here, this is interesting because it looks like it fits in this pi range, but we have to remember a period is everything repeating. So we're not just including only this pi over 2, we're also going to include this one. So let's try that. Oops, I should have done it with this one. So if we were to add these two together, pi over 2 plus 3 pi over 2, that's 4 pi over 2. And we're adding it even though it's negative because we're trying to figure out how far from, let me do this, how far from here to here plus here to here. We're trying to figure out how wide it is. So this right here, 4 pi over 2, that's going to be 2 pi. So our period is 2 pi. I have a feeling it's going to be the same thing for cosecant, not just because I've done these problems like a bunch of times, but just because, remember, it's kind of like the backwards version. It's a reciprocal of, it's cosecant, it's a reciprocal of sine. So if sine has a period of pi over 2, or 2 pi, if sine has a period of 2 pi, then cosine, which is a reciprocal, should also have a 2 pi. And that makes sense because it's at 5. 2 times pi is 6.28 something, I think. So I'm just going to go ahead and say it's 2 pi as well. So if cosine is a reciprocal of tangent, it should also be pi. But let's just check it just to be safe. It looks like it's pi. It goes from 0 to pi. And just to verify, I'm going to do this at pi. So I made a vertical line using x equals. And I can see that it looks like it does not cross that, meaning that it starts from 0 and it goes all the way to pi. So this one is pi. And that's how we figure it out. So it's like copy and paste the graph of each function. Ooh. You guys can do that. I haven't been doing it. I don't even think it gives you a tool to, I guess, screenshot it. Yeah, you're going to have to screenshot it. So you can use this to graph if you want. Graph new equation. And then just screenshot it and cut a picture of this and paste it onto here. Did you guys need me to go over how to do a picture? Or do you guys remember how to do it from here? Okay, cool. And then our next question is, what if we put two sine? So let's see with 2 sine. Does multiplying by 2 change our period? It doesn't. Or does it? Let's check. And you guys don't have to do this. I just like doing it because it makes it very clear. So yeah, it goes from here and then it starts repeating after 2 pi. So from 0 to 2 pi. So that's our period. Our period is still 2 pi. So all of our answers should stay the same. 2 pi. Oh, I can't copy it from there because that's the sample answer. I'm going to put 2 pi here. What if I have 3 cosine? Maybe 2 didn't change it, but maybe the 3 for cosine changes it. Nope. Looks like it repeats. Again, it starts at 1, and it looks like it's back at 1. The only thing that's changing, it looks like, is the amplitude, how tall it is. Remember, it only went up to 1 before, but if we're multiplying by 3, that 1 becomes a 3. So it's still 2 pi. And this one, well, tangent was pi. So I have a feeling it's still pi, but give me a second here. Let me copy this down. We know it's still going to be it because we're just changing the amplitude, but let's see how it changes. 3 tangent of x. If we look at it, it just looks like it curves more. Let's look at a regular tangent of x. Yep, it just curves a lot more. Why is this? They couldn't have picked a better color. There we go. So it's steeper because the amplitude is steeper. I'll go more over or I'm sure Edmonton will go over amplitude. So in question 2, um, compare the periods. What can you conclude? So the periods are the same. Same. So multiplying a coefficient, because remember, numbers in front are called coefficient, a coefficient by a trig function does not change the period. That's all that happens. Multiplying it doesn't change the period. They're just asking us to say what we can conclude. We can say that it only changes the amplitude. And the idea of saying an amplitude is how much it amplifies it, right? How tall it grows. So if this is a regular cosine, it still has the same points where it crosses, but it just doesn't go as high. And with tangent, it just grows bigger. Well, I can't draw, but you guys get the idea. So let's see what happens here. What happens when we put a sine plus x? Oh, this is terrible. I want to say, okay. So this one's kind of important. Do not put the parentheses when you're doing this one. I imagine later on they're going to show us the one with parentheses. So this is bad. They really should have put a parentheses in the middle of the x, because it's a huge difference. So let's say I'm lazy and I'm just going to copy this into Desmos, because Desmos is way better than the other one. We see that it just moves it up. The period is still exactly the same. It's still at 2 pi. So it's still there. So if we go here, that's 0. So it's still at 2. The only difference is it went up 2. So again, we're just going to copy the 2 pi. Copy the 2 pi. I'm debating if it would be faster if I do it the other way. Secant is the opposite of cosine, right? Or not the opposite, the reciprocal of cosine. So if we change this to a plus 3 and we change this to secant, plus 3, not plus c, we see that everything kind of just went up 3. I don't know why I went. Oh, that's right. It went up 3 because before it was at -1. This one was at 1, so now it's at 4. Everything went up 1. So it is still pi over 2. Cotangent, you get the idea. This is going to be just pi. I feel like Adventum sometimes draws out these lessons so long that you get bored by the time you see it. But you can graph them. Make sure you're showing your pictures. I just don't want to upload and take up like all the time just uploading pictures. Compare the periods of the functions to the original. All right, so what we can do is, since I'm lazy, I'm just going to copy this. The periods are the same. Nothing's really changed. The only difference is it only changes I would say, y-intercept. It only changes the y-intercept. It doesn't even change it. It changes the y-intercept. It doesn't only change the y-intercept because everything goes up. If everything's going up, everything's moving along with it. So I would say which vertically changes the function, or which vertically translates. Get all fancy with our words. Translation means moving it up, down, left, right, diagonal, all that stuff. So it's a translation. Now we're going to consider it with parentheses. This is why I was saying, like, hey, they should have really put parentheses here, because now we're going to see the difference with parentheses. All right, so let's take this function. I wonder if Desmos is going to understand the pi. Desmos doesn't even want me to copy this. Desmos, why? Oh, but you know what I can do? Copy from the equation. And no, I can't. Adventum, why you do this? Oh man, Adventum has this as a picture. It doesn't have it as an equation. No. All right, sine x plus 2 pi. Sine of x plus 2 pi. So if we look here, we see that, wait a minute, what's happening here? This crosses the x-axis still at 2 pi. But something weird happened. It looked like nothing happened at all. What if I only changed the pi though? Oh, it looks like it shifts it. But the thing is, we shifted it an entire unit circle. So even though it looks like nothing happened, it moved over 2 pi. So it looks like nothing happened because it moved over enough where it just keeps repeating again. So what's the period? Well, the period is also still 2 pi. Oops, not that. Period is still 2 pi. Nothing happened. Well, what happens if we move tangent over just pi? Remember, the period of tangent was pi. So if we move it over just pi, I don't know why they're going really slow about this. I thought they were going to actually move it over, and then they didn't. So it looks like nothing's happening. So this is still pi. Our period still has not changed. Next one is 3 pi. Oh, wait. Now we're getting somewhere. Probably would have been faster for me to type it. Would have definitely been faster for me to type it. 3 pi. So if we look at this, remember sine usually starts at 0, but it goes up. This one starts at 0, but it's going down, so it's shifted over. Darn it. You know what? I guess it is faster for me to just do this. All right, 2 pi. So, and then again, copy and paste the images. So this one, compare the periods of these functions. Oh, again, the periods aren't changing, so I'm going to take the lazy way out and just copy this. Periods are the same. Oh, shoot, I just realized I haven't been doing this. So adding adding a coefficient to a trig function doesn't change anything, only changes it vertically. This one, I'm going to say, so adding a coefficient to the, oh shoot, I have it on insert. No. To the angle, because we're adding something to the angle. Does not change the period. It changes the movement left And right. And they gave us bad examples because, like I said, the only one we can really see that it changed was this one. So I really wish they would have given us something else so we can actually see it moving. They should have given us the same function. But you guys just know if you're adding something to the x, it's going to shift it left. If you're subtracting something from the x, it moves it to the right. It's always backwards of what you think it's going to be for x, only for x. So let's see what happens when we multiply by x. I know we kind of went over how multiplying is going to make the period shorter because it's faster, but Momentum takes a while to teach us things. Oh, this one I can actually do. Sweet. All right. So if I do this, it's a lot shorter. This is our 2 pi line right here. But we see we have 1, 2 periods. So it cut the period in half. Now the period's at pi because it's going to start repeating. So from here to here is going to be a repetition of here to here. So this did change it. It changed it to pi. And this one is probably going to change it a lot smaller. So give me a second. What was it? Cosine 3x. So we're going to change this to cosine 3x. And we see here that, okay, so if it starts here, then the next period starts right here. So it changed the period to pi, 2 pi over 3. So we're dividing it by 3. So our period changed to fraction 2 pi over 3. And then here, well, if our period was pi before and we're multiplying it by 4, this means we're probably going to end up dividing by 4. So it's probably going to be pi over 4, but let's verify it. Ooh. And the only way to really verify this is you can't make it all fancy and just click on it. So we can just try to attempt to make an asymptote. Oh, what is happening here? It doesn't look like. Oh, wait, they're pi over 8, x equals pi over 8. And then negative pi over 8 x equals. So it is pi over 4. The only difference is it's kind of tangent starts off at the negative part. But if I did this, okay, I was looking at this, x equals pi over 4. I see that it cuts it right down the middle. So it would be technically correct to show it that way because we can see it starts here and it starts here and it grows, starts here and it grows. So it is every pi over 4. So our period is pi over 4. It just looks a little weird cutting it in half that way. So period is fraction pi over 4. All right, and now we're going to compare those. So you can tell something was supposed to happen because this one said compare all functions. Compare this function. The period of, I'm just going to say sine 2x. There's no point in saying y. Sine 2x is half of that of sine x. Half, I don't like this, that of. Is half of sine x. All they had asked us to say. What about this one? My laziness comes into play here. The period of that, so we're going to change this to cosine 3, is a third. We're dividing it by 4. Cosine. compare tangent x. So this we're going to say the period of tangent 4 is a fourth of tangent x. Based on the answer to the blah, find out. So now it's going to ask us for the rule. So what we're going to say here is when we add a number, or not add a number, blah. When we, did I mess up on the last one? I'm starting to think. When we shoot, this one wasn't supposed to be multiplied. I'm so sorry. So, so adding a number to a coefficient. So in this one, it's when we multiply a number. And just in case you guys didn't catch that, sorry, I did it really fast. This one was supposed to be adding for question 4, part B, when we're adding a coefficient. I don't know why I put multiplying. I think I forgot to change it. This is to the function. This one's to the angle. So when we add a number to the when we multiply a number to the angle, it divides the period by that number. So what I mean by angle is that theta, that tangent of x. We're multiplying it by 4, so the period gets cut to a fourth. And that's, like I said, it acts 4 times faster, so the period is 4 times shorter. So we're dividing it. Is that making sense? Sorry, I know I went through that whole thing, and it was kind of boring until we finally got, well, even when we got to the difference, it was still boring, I'm not going to lie. But does that make sense? So that's the only time our period changes is when we're multiplying by the angle, something by the angle. All right, so here they're going to teach us, since I scroll up, I don't know why, for some reason my pen thingy like always moves it down. So here we're learning about our periods. So our periods are for our regular functions. It's 2 pi. They're normally 2 pi. Tangent's a little different. And the reason why it's different is because of the critical points. They change for tangent. Since we're doing tangent is y divided by x, basically. Well, here we're going to have this, what is it? X is 1. So we have 0 over 1, right? But over here, we have 1 over 0, so it's undefined. So that's why a pi over 2, we get an asymptote. And then over here, we're going to have -1 on the bottom and 0 on the top. So it's 0 again. So that's why over here it's at 0 at pi. So that's why it keeps getting cut in half, because every time we get to these 2 points, the tangent is undefined. So it's cut a lot shorter. While the other trig functions have the luxury of going every pi before they get to a 0, this one gets undefined every pi over 2. So here, again, this is also 2 pi because it's sine, the reciprocal of sine. So remember, secant is always 1 over cosine, sorry. And then cosecant is 1 over sine. So they do have the same period. And then cotangent, that's just 1 over tangent. That's how come the zeros of cosine, because remember at 0, this was a 0 for tangent. It becomes an asymptote for cotangent, because we're basically taking that 0 over 1 and flipping over to 1 over 0 for cotangent. All right, moving on. So this is what's happening. They're changing the amplitude. So when you multiply a function by a number, it changes the amplitude. When you add a number to the function, remember, we're talking to the function, the entire function, not the x value, not the input. It moves it up. When we add something to the angle itself, the x value, our independent variable, all the ways of saying it, that's going to move it left to right. So the general form for this is this a sine of bx plus c plus d. This changes our amplitude. This changes our period. We haven't discussed that on these slides yet. This changes our horizontal. Technically, it's called a phase shift because there's a bunch of things that happen if we change the period and the horizontal and the phase shift. I don't know if you guys studied this in algebra 2, right, Nick? Phase shift. Was your honesty gonna be like, I don't remember algebra 2? So it's our phase shift. It's how it moves. But sometimes when we have a period change and a phase shift, it doesn't exactly move horizontally the way it should. It's really weird. I don't like it, but it's how math works. So I can't really do anything about it. I'll show you guys a little shortcut I learned about it. And then our D, in this case, this changes our vertical shift. This is not affected by the A, luckily. The C, changing it left and right, is kind of affected by the period because obviously if the period changes our starting point, it kind of changes the phase shift a lot. It's very weird. If you factor it out, it's a lot easier. I'll show you guys how to do that when we get to that point. So this is talking about how it changes our period. It's this idea of 2 pi divided by c, and that c comes from what I did over here. Oh, actually, I don't know where they got c. I call it b. I don't know where they got. Oh yeah, derp. Yeah, c. Wait, no. I have no idea what they're doing. That's weird. I would call it b. That's just Edmentum being Edmentum. I'm sorry, guys. So we're just going to divide it by whatever is being multiplied by that x. All right, so let's do an example problem. All right, so which one of these is cotangent a period of? Okay, so normally cotangent does have a period of pi. The period, when it repeats, of pi. So this is an answer because it only changes how up and down it goes. I know that's a sine function. I just didn't want to draw a cosine or cotangent function. This one, this is changing the period, so that's no good. This one's okay because this is only moving left or right. In the case that it's plus, it's moving it to the left, but it doesn't change the period. This is changing the period because it's multiplying our angle by something, so that's no good. Nothing's being multiplied by the angle. It is multiplying the function, but again, that only changes the amplitude. So that one's okay. So we're going to click this one, and this one. Submit it. Boom. And then, as always, guys, check out your summary for this so you guys can understand your test. Nick, you weren't here, but hopefully you were paying attention on Monday because I forgot to hit the save button on that video. So if